All right, so we have a 75 kilogram guy steps out of a window. I can't draw that. So he's gonna jump off of this cliff 1 meter high onto the ground below. The first question: what is his speed just before his feet strike the pavement? So you could have done this with kinematics, right? You could do this with just a motion equation. But how would you do this chapter 5 style? So look, he goes like this. He goes down to the ground. So for that part, is it conservative or non-conservative? It's conservative. And what do I mean by conservative? The only force doing work is gravity or spring. What's the only force doing work as he falls to the ground? Gravity. So it's conservative. So for part A, like I said, you could have just used a kinematic. But if you want to show this chapter 5 style, you go, okay, mechanical initial plus or minus work non-conservative equals mechanical energy final. There is no non-conservative for that first part, okay? And then how many types of mechanical energy are there? 3. I'm just going to leave spring off because there's no spring here. So this becomes kinetic initial plus potential of gravity initial. And then this is kinetic final plus potential of gravity final. Okay, so you got to set your 0 point. Whenever you do potential of gravity, you need a 0 point. So where's the 0 point going to go? I'd put it at the lowest point. The best place to put your 0 point is at the lowest point in the problem. So down there is h equals 0. So up here, what type of energy does he not have? He starts from rest. Does it say that? He steps out. So that kind of implies, where does it say? Does it say from rest? Right there, yeah, from rest. Okay, so he starts from rest. That means no kinetic initial. All right, when he hits the ground, and actually what we mean is like a split second before. A split second before he hits the ground, what's going to be 0? Potential of gravity, because he came down to the 0 point. So basically what we have is potential of gravity initial is going to equal kinetic final, and then you plug in. Potential of gravity is mgh, kinetic is 1/2 mv squared. The m's cancel here. So his velocity right when he hits the ground, the moment he hits the ground, is going to be square root 2gh. By the way, let me show you something cool. I don't know if you noticed this. If you did this with a kinematic, you would have gone Vf squared equals V initial squared plus 2G, 2A, so 2GH. That's a kinematic there. V initial is 0, so look, what's V final? You get the same thing with a kinematic. Pretty cool. Okay, so you plug in, square root 2 times 9.8. H is 1, so he hits with a velocity of 4.43 meter per second. Okay, that's the easy part. Now, part B is a little trickier. So in part B, what they're saying is, all right, so now he goes down, and then boom, when he hits the ground, he has his knees and ankles locked. This just sounds painful. The only cushion for his fall is 0.5 centimeter give in the pads of his feet. Okay, so when he hits the ground, his stopping distance, so you got to really try to magnify that. The distance that he's going to stop, let's call that delta x. Delta x is going to be equal to 0.5 centimeter, which is 0.005 meters. That's his stopping distance. All right, so if we look at the guy as he's being stopped, what are the two forces on him as he's being brought to rest, right? So he jumps from up here and he goes faster, 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 and then bam, he hits the ground. What are the two forces on him when he hits the ground? Mg down, and then what's up? the normal force, right? Now, force of gravity, is it conservative or not conservative? This mg here, conservative or not conservative? That's conservative, right? Didn't we have that when he was falling? When the guy was falling, we had mg. Now, normal force, conservative or not conservative? It's not conservative. So, we got to account for it. But look, before I set this up, could you have solved this a different way? You could have done this chapter 4 style. You could have gone like this. You could have been like, all right, because, well, first of all, what are we looking for? It says calculate the average force exerted on him by the ground. So what are they talking about there? If they say find the force exerted on him by the ground, what force is that? Not the net force, the normal force. The net force, F net, the net force would be normal force minus mg. That's the net force. When they say find the force exerted on him by the ground, they're talking about this guy. They want us to solve for the normal force. So how could we find the normal force? A different way. Well, what you could have done, you could have gone, all right, sum of the forces equals normal force minus mg. That equals ma, right? And we're saying that up is plus and down is minus, okay? And then use a kinematic to get a, right? Could you find the acceleration with a kinematic? Yeah. What's his initial velocity? Like right before he hits the ground, what's v initial right before he hits? 4.43 negative. Why negative? He's going down. What's v final? 0. And then what's the stopping distance? 0.005. That's enough to get the acceleration, right? And then you could solve for it that way. But let's do it chapter 5 style. So chapter 5 style would look like this, because you got to be able to do it both ways. So chapter 5, you would go like this. Mechanical energy initial plus or minus work non-conservative equals mechanical final. Now, dudes, do we have a non-conservative force? Yeah. What's the non-conservative force here? The normal force. Anything that's not gravity or spring is non-conservative. All right, so let's call it what it is. This non-conservative force here is what? The normal force. I'm going to put Wn. N stands for what? N equals normal. All right, so dude, where should the initial be? I would just keep the initial up here. Could you have made where's another place you could have made the initial? You could have made the initial right there, like the split second before he hits the ground. Either one's fine. So let's say that his initial is up here. Here's his initial. And then his final is going to be when he stops, right? That's going to be the final. All right, what's the only mechanical energy he starts with? Potential of gravity, right? That's no kinetic up there. So he starts with potential of gravity. Now, is work non-conservative going to be plus or minus? No, I don't want to buy any candy.
Well, I know.
Oh, I'm just kidding.
Anyone else want
All
to buy
right.
some candy? I got it.
Hey, man, we're doing physics here, dude. This guy. All right. Okay. Boy, the candy's out in force, man. There's like candies everywhere. All right, so where were we? Okay, is this work non-conservative? Is it plus or minus? Is the normal force going to add mechanical energy or remove it? It's going to remove it. So we're going to go minus work of the normal force. All right, what's the mechanical final? When he stops, he hits the ground, stops. What's the mechanical final? 0. Does he have potential? No. Does he have kinetic? No. So basically what we're saying is this. The potential of gravity initial is equal to the work done by the normal force, right? How much of the mechanical energy does the normal force take? all of it. The normal force takes all of it. Okay, so this is going to be mgh. Now, what can we plug in for work of normal force? That's going to be, so what's the work equation? Force of normal times displacement. Are those parallel to each other? Is the normal force parallel to the displacement? Yep. Okay, now we're ready. Oh, and then look. Shouldn't this be negative right here? The work done by the normal force? Isn't it opposite motion? Yeah, but we already called it negative right here. We already called it negative. Okay, so the normal force is going to be mgh over the displacement. So the mass is 75. Okay, I'm going to leave units off. Bad physics. Bad. I'm out of room here. 9.8. What's h? 1. What's the delta x? 0.005. Dude, I'm going to get fired. Why am I getting fired? No units, dude. If Mrs. Crest sees this, she's going to be like, Spalding, look, in my office. Number 61, you left units off. Monday's your last day. So this comes out as 147,000 newtons. That's force, man. You know, if you convert that to pounds, if you convert this to pounds, it's about 33,000 pounds. 33,000 pounds of force. That would hurt.